Hello friends, welcome to my lecture on planar graphs. Let us define a planar graph. A graph G is called planar if there exists some geometric representation of G which can be drawn on a plane such that no two of its edges intersect except only at the common vertex. The points of intersection are called crossovers. The graph K4, okay, let us look at the graph K4. K4 as we remember is a Kn is called a complete graph with n vertices. And a graph is called complete if every vertex is related to is joined to every other vertex. Okay. So, here let us look at the graph K4. Here you can see this is the graph K4. Okay. Here every vertex is joined to every other vertex. Now, it is a planar graph because you can see no two of its edges. Okay. No two of its edges. Now, here this is not a planar graph because two edges here, this edge and this edge, they are intersecting each other, but this can be made, okay, a planar graph by taking this edge, this edge as like this. Okay. If we can if we draw this edge like this, then it becomes a planar graph. So, this is a complete graph, this is a graph K4. Okay. It can be made a planar graph like this. Okay. So, the graph K4 which is a planar graph is usually drawn with crossing edges as shown in the figure below. Draw the graph so that none of its edges cross. Okay. So, you can see this here in the complete graph K4, the two edges are cross each other. Okay. So, here we can make it a planar graph, okay, when we join this vertex and this vertex in this manner, then this edge and this edge do not cross each other. So, graph K4 is a planar graph in this case. Now, let us see this one, this graph. Okay. This graph is a planar graph because none of its edges cross. As such, we are seeing that its edges are crossing, but we can draw it like this. Okay. So, this and this, they are these ones. Okay. These ones, this one and this one. Okay. This one, they are these ones and this one, and this edge, okay, we can join like this. This edge is like this, this is joined like this, and this one, this edge is joined like this. Okay. So, since this graph, okay, can be made in such a way that none of its edges cross, so it is a planar graph. Draw the planar graph shown in the figure below so that none of its edges cross. Now, here we can see this as such, we are seeing that the edges cross here each other, but it can be made in such a way that its edges do not cross each other. So, this and this, okay, they are here. Okay. And this vertex, let us bring down here. Okay. So, that when it comes down, this can be joined to this, and this can be joined to this, and this can be joined to this. If you draw this vertex down here, okay, then these edges which are joining to it, okay, this one and okay, this one and this one, okay, they will come here like this. Okay. And by drawing graph in a different way like this, we see that none of its edges cross. So, what do we see here, that it looks like that the edges cross each other, but they are not crossing each other. And so, in the case of this graph which is K4, in the case of this graph, okay, and in the case of the third one, this one, all graphs are planar graphs. Okay. We can draw them in such a way that none of their edges cross. Now, let us discuss maps and regions. A particular planar representation of a finite planar multigraph is called a map. We say that the map is connected if the underlying multigraph is connected. Now, region, a given map divides the plane into various regions. For example, the map in this figure below with 6 vertices, there you can see there are 6 vertices A, B, C, D, E and F. There are 6 vertices and there are 9 edges. Okay. Edges are see AB, BC, okay, CE, we have CD, we have DE, we have BD, we have AE, we have D, D we have taken, AD we have AD, okay, and then FE. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 edges are there, and there are 6 vertices. A vertices are A, B, C, D, E, F. Now, this graph divides the plane into 5 regions. Regions are R1, R2, R3, R4 and R5. Okay. The border of each region of a map consists of edges. We can see that border of R1. Border of R1 is border of R1 consists of edges AB, BD and AD. If you look at R2, okay, then the border of R2 region is consists of edges BC, CD, BD. Okay. Likewise, if you see the R3 region, okay, R3 region, border of R3. Okay, border of R3 is consists of edges CE, okay, then CD, then D, okay, then EF and FE. Because it can be considered as a closed path. If you start with C, say with the vertex C, then you follow CD, DE, EF, then FE, then EC. We can start with C and reach C. Only what we have to do is we have to move in the direction EF and then again in the direction, then back in the from F to E. Okay. So, by following the path CD, DE, EF, FE, okay, EC, we can go to C, and therefore, it is a closed path. So, R3 is bounded by the border of R3 consists of edges CD, DE, EF, FE and C. And similarly, say if you take R say your R4. R4 is has border the edges on its border as AB, AC, AE, CE and BC. Okay. The border of R4. Border of R4 consists of the edges AB, AE, AB, BC and CE. And if you look at the border of R5, okay, border of R5. Okay, border of R5 consists of edges AE, then ED and then AD. Okay, consists of edges AE, ED, AD. Now, here the edges EF and FE, will be considered as same because we are not associating direction with it. Now, sometimes the edges will form a cycle, but sometimes not. Okay. The edges will form a cycle, but sometimes not. For example, in the figure below, the borders of all the regions are cycle except for R 3. Okay. So, let us see how they are cycles. Okay. For R 1, let us see the cycle. So, R 1, the cycle is A B D A, A B D A. Okay. For R 2, B C D again cycle, B C D B, okay, because cycle is a closed path. And then we have R 3. Okay. In the case of R 3, we have it, although it is a closed path, but it is not a cycle, because we follow C D, then D E, then E F, then F E. Okay. So, that we cannot do in the case of a cycle. So, R 3 the border of R 3, okay, border of R 3 is not a cycle. While if you take R 4, the region is again a cycle, because we can follow A B, B C, C E and then E A. Okay. So, so all others are cycles, the borders of all other regions are cycles except R 3. Now, however, if we do move counterclockwise around R 3, starting say at the vertex C, then we obtain the closed path, okay, C D E F C, where the edge E F occurs twice by the degree of a region R. Okay. Degree of R, we mean the length of the cycle R closed walk which borders R. So, let us see, we can find the degree of the vertex here, degree of the region, degree of R 1 is how much? Degree of R 1, you see we have by the degree of region R, written as degree of R, degree R, we mean the length of the cycle R closed walk which borders R. So, length of the cycle here is what? 1 A B, B C, B D, D A, okay, that is 3. Length of degree of R 1 is equal to 3, okay, and degree of R 2, region R 2 is also 3, B C D V. Degree of R 4. Okay. Now, we mean the length of the cycle R closed walk. Okay. So, here in the case of R 3, so C D, then D E, then E F, then F E, then E C. So, we have 1, 2, 3, 4, 5. So, degree of R 3, degree of R 3, okay, we are writing degree of R 3. Degree of R 3 is equal to yeah. So, C D, D E, E F, F E. Okay. That means, we are going from E to E, okay, and then F to E. So, 1, 2, 3, 4, 5, okay, and then we have degree of R 4. Okay. So, A B, B C, C D E and then E S, 1, 2, 3, 4 and degree of R 5. You see R 5, A D, D E, E A, so 3. Now, sum of the degrees of the regions is how much? Sum of degrees of R 1, R 2, R 3, R 4, R 5. This is equal to 3 plus 3 is 6, 6, 5, 11, 11 plus 4, 15, 3, 18. Okay. And number of edges here are number of edges here is 9. Okay. So, it is twice the number of edges, 2 times number of edges of the graph. Okay. So, in the case of a graph, the sum of the degrees of the regions of the graph okay, is equal to twice the number of edges of the graph. So, we have this, find the degree of each region of the map in the figure below. We have found the degrees of the regions, various regions here, the same graph we have here, okay. And then the sum of the degrees of the regions of a map is equal to twice the number of edges, that we have verified, okay, here for this case, okay. Now, let us see the proof. Each edge E of the map either borders two regions or is contained in a region, okay, and will therefore occur twice, okay, in any path along the border of that region. Say for example, here you can see this one, okay, this BC you can see. BC is a part of the boundary of this R4, and also it is a part of the boundary of R2. So, it will be counted twice, okay, towards the sum of the degrees of the regions. And then if you see, if an edge is contained in a region like FE is contained in this region, then again it is counted twice. You can see here we moved from E to F, then back from F to E. So, it is counted twice. So, in order to count the find the degree of R3, we had to count E of twice. So, each edge E of the map M either borders two regions or is contained in a region and will therefore occur twice in any path along the border of that region. Thus, every edge contained in a region will be counted twice in determining the degrees of the regions of M, and so sum of the degrees of the regions of a map is equal to twice the number of edges. Now, identify the cycle or closed path that borders each region of the map given in the figure below. Further, find the degree of each regions of the map. So, let us first find for R1 what is the cycle. R1, okay. Cycle is A B G F A, A B G F A, A B G F A, and for R2, okay, for the region R2 we have closed path, okay, because DH is contained in the region R2. So, BC, so it is a closed path, okay, it is not a cycle. We have BC, HD, HDH, G, B, okay, BC, HD, H, G, B, okay, that is the boundary of region R2 and then R3. So, we have cycle CE, H, C. CHC, okay, R4, okay, we have taken R1, R2, R3, now this is R4, okay. So, we have AB, it is again a cycle, and we have ABC, ABCE, H, then G, then F, and then A, okay. So, this is the now for degree, as regards degree of R1, degree of R1 equal to 4, 1, 2, 3, 4, degree of R2 1, 2, 3, 4, 5, 6, okay. So, we have 6 because we have DH have to be moved twice, okay. So, it is 6, degree of R3 1, 2, 3, and degree of R4. So, AB, BC, CD, CE. So, 1, 2, 3, 4, 5, 6, 7. Okay. So, sum of degrees will be equal to sum of degrees of regions of this map is equal to 4 plus 6, 10, 10 plus 3, 13 plus 7, 20, okay, and edges are how many? Number of edges. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, number of edges are 10. So, sum of degrees of the regions of this map is equal to twice the number of edges. Now, Euler's formula. Euler gave a formula which connects the number V of vertices, okay, number V of vertices, the number E of edges and the number R of regions of any connected map. Specifically, he proved that let M be a connected map with B vertices, E edges, R regions, then B minus E plus R equal to 2. We can verify this formula for the map we have just now discussed. So, V is the number of vertices. Okay. So, there are how many vertices? 4 A, okay, A 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices are there. So, B equal to 8. Okay. And then E is the number of edges. Okay, number of edges are 10. So, E equal to 10. And the number of R is number of regions. There are 1, 2, 3, 4. 4 regions are there. So, R equal to 4. Okay. So, B minus E plus R equal to 8 plus 4, 8 minus 10 plus 4 equal to 2. Okay. So, that this example verifies this theorem. Find the number B of vertices, E of edges, R of regions of each map in the figure below and verify Euler's formula. Now, let us see here. So, there are 5 vertices 1, 2, 3, 4, 5, okay. B equal to 5 and then number of edges are 1, 2, 3, 4, 5, 6, 7, 8. So, we have edges equal to 8. Okay. Regions are 1, 2, 3, 4 and one region outside 5. Okay. So, R equal to 5. So, then B minus E plus R. Edges are number edges of, okay. So, 5 minus 8 plus 5, okay, equal to 2. Okay. So, that verifies the formula and here how many vertices are there? 1, 2, 3, 3, 6, 3, 9, 3, 12. So, B equal to 12 for the part B. Okay. B and then edges are how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So, 17. Okay. So, edges are 17. Okay. And then regions are how many? Are 1, 2, 3, 4, 5, 6 and one region outside. Okay. So, 7. So, what do we have here? B minus E plus R equal to 12 minus 17 plus 7. So, that is equal to 2. Okay. And then for this, okay. So, vertices are for part C, vertices are 1, 2, 3. There are 3 vertices. Okay. And E is equal to 1, 2, 3 and this one 4. Okay. 4, this one 5, this one 6. So, we have 6 edges. Okay. 1, 2, 3, 4, 5, 6. Okay. And then regions are 1, 2, 3, 4 and one outside 5. So, we have B minus E plus R equal to 3 plus minus 6 plus 5, okay, and we get 2. So, these maps verify the Euler's formula. Find the number B of vertices, E of edges, R of regions of each map in the figure below and verify Euler's formula. For example, this one here we have 4 vertices. Okay. So, B equal to 4, E equal to 4 because there are 4 edges. Okay. Regions are 2, 1 here, 1 outside. So, r equal to 2. We have 4 vertices, 4 edges, okay, and regions are 2. So, V minus E plus R, yeah, 4 minus 4 plus 2 equal to 2. Okay. Now, here 1, 2, 3, 4, 5, B equal to 5, okay, and E edges are 1, 2, 3, 4, 5, 6, 7, 8, 8 edges are there, and regions are 1, 2, 3, 4 and 5. Okay. So, we have B minus E plus R equal to 2. Okay. And now, let us take the last case. Okay. We have 1, 2, 3, 4, B equal to 4 in part C, okay. And we have E equal to 1, 2, 3, 4, 5 and then 6, 7, 8, 9, 9 edges are there, okay. And regions are 1, 2, 3, 4, 5, 6 and 1 outside 7. So, we get B minus E plus R equal to 2. Okay. So, this also verifies the Euler's formula. So, that is all in this lecture. Thank you very much for your attention.